we're going to look at something called L'Hopital's rule, and this is the situation we've looked at before. And the problem is that if we plugged in x is equal to 0, you know very well that would give us a 0 on the top and a 0 on the bottom. But the other day we talked about linearization, and we talked about the fact that sine of x can be approximated near x is equal to 0 by just y is equal to x. So we would expect that these two functions, sine of x and x, are going to behave almost identically near x is equal to 0. So it makes sense that the ratio of the two would be equal to 1. And that's something else that we had proved earlier by using the sandwich theorem. Well, we're going to use something called L'Hopital's rule also to demonstrate this. And if you're using L'Hopital's rule, it's always a situation where you have something in indeterminate form, 0 over 0, and you're going to use derivatives. And rather than using the quotient rule, we don't use the quotient rule, we just take the derivative of the top function and the derivative of the bottom function, and then plug in x is equal to 0. So this, in fact, is going to give us cosine 0 over 1, which is just 1 over 1, which is something that we would have assumed based on what we had spoken about. So here's the situation with L'Hopital's rule. It always starts with an indeterminate form situation. So you're looking for the limit as x approaches some number of f of x over g of x, right? But the problem is f of a equals 0 and g of a is equal to 0. So what we do in this situation is, if it's indeterminate form, we just take the derivative of the top and plug in a, the derivative of the bottom and plug in a. And whatever we get for that, well, that should be the limit of the original situation. That's L'Hopital's rule. And you would be wondering, why are we doing this now? We're talking about linearization. What does this have to do with limits? And here's what it is. Again, for L'Hopital's rule, we're looking for the limit as x approaches a of f of x over g of x. And I'll say again, I'll spell it out, but f of a is the same as g of a, which is 0. So this is a little bit of a problem. Here's what we can do, though. Near x is equal to a, we can approximate these difficult functions by using the tangent line. So what we know is near x is equal to a. Well, here's what we have. Whatever this function is, we have the derivative of the tangent line. And we know we have an ordered pair, a, f of a. And what we can do is approximate this using a tangent line approximation. So we have y minus, let's see, f of a is equal to the derivative times x minus a. So in other words, on the tangent line, y is f of a plus f prime of a, x minus a. So basically, this is the equation for our tangent line. We can also find the equation for a tangent line of g of x, right? That's going to give us g of a plus g prime of a times x minus a. Well, here's what we can do. So here we are taking the limit as x approaches a of f of x over g of x. And as long as we're very close to x is equal to a, we might as well use the tangent line approximations. So this is basically going to be f of x. I'm going to replace this f of x with f of a plus f prime of a times x minus a. And in the denominator, same thing. X is very close to a, so we can just use the linear approximation for g. But you, of course, are thinking ahead. This is what we had originally. And we already said f of a is 0 and g of a is 0. So that our numerator, then, is going to simplify just into, f prime of a times x minus a over g prime of a times x minus a. And obviously, the x minus a's cancel, so what we are left with is f prime of a all over g prime of a. So the limit as x approaches a of f of x of g of x in indeterminate form situation simplifies into just the derivative of the top over the derivative of the bottom.